All right. Good morning, everyone. Everybody ready to start with the morning program? Everybody paying attention? Some people on their cell phone. Can I have your cell phone, please? This will only take a moment. I saw the quick tweet. Oh, fine. Hold on. Oh, excellent. Here. Next. Talking with Gary at the Hadoop Summit. Retweet this, then turn off your phone and pay attention. Excellent. All right. Thank you.
So good morning, everyone. Thanks for joining us. We would like to tell you a little story about our poor MapReduce user, Edgar, and how we can hopefully make his life a little bit better. I'm Gary Helmling. I'm an Apache HBase committer and PMC member. I work at Twitter on the core storage team, focusing on Hadoop and HBase.
I'm Joep Rottinghuis. I started out as a software engineer at Twitter. Now I manage the HBase Hadoop team at Twitter. So this is roughly the table of contents of our talk that we want to go through today. So first we want to lay out the problem. Then Gary will explain why hRaven. We'll then explain how it works, and then we'll go in two pieces. I'll first explain a little bit how we load data, and then Gary is going to go into the table structure and querying part. We'll then talk about how we currently use hRaven and explain what some of the future work is that we'll be working on. So first of all, the problem. What problem are we trying to solve? So when we think about how we use our clusters, there's somewhat of a mismatch in abstractions. On the one hand, users run pig and Scalding scripts and not straight MapReduce jobs, by and large, on our clusters. Yet the JobTracker UI shows individual jobs, not a DAG of all of the jobs that are generated by pig and Scalding. So there's a mismatch between what the users are doing and what the cluster is showing them. Furthermore, we have a problem with scale. If you're running tens of thousands of jobs on a cluster, and this is a familiar snapshot from a JobTracker, then if you want to see what jobs have been running and you want to see what the status is, you need to go click through. So this is a snapshot on the top side of the job history page, and you can see in this particular case, in the area that we've run 50,000 jobs so far, and you see pages on the bottom. You see it blown up where you have to click on next, next, next to go find where your job is. And as you have a lot of jobs come in, by the time you end up actually clicking to the page where your job was before, it's going to scroll right off. And on our clusters, actually, the JobTracker stays up for a long time, and in some cases, it's actually stayed up for more than 1 million jobs. So there are several questions that our users want to be able to ask and that we have a hard time answering. So some of the questions are, how many pig jobs do we run versus Scalding jobs? Another question is, what capacity do my jobs take on the cluster? How much of the pool am I using that have been allocated? And generically, questions of how many jobs do we run in a day? So going back to the JobTracker and clicking through and counting these things is not very feasible there. Questions like, what percent of our jobs are very large jobs, and what percentage are very small jobs? And then one of my favorite questions I had when I was chatting with one of our engineers, and I was explaining him how you can tune the MapReduce framework, you can set the IO sort percent and spill records, and you can tune and tweak all these things. He said, why do I have to hand tune all of these hundreds of jobs? Can't the cluster just learn by itself? So then, with our hRaven, the answer is nevermore.
So now that you've seen the kinds of questions we're dealing with, we'll talk about how hRaven addresses these problems. First of all, it stores all of the data that we're concerned with, so all of the stats, job counters, job configuration, and job history logs for every MapReduce job that we run on the cluster. Secondly, it matches the user experience in that it's structured around the full DAG of jobs that are run by a pig or Scalding application, and not just around individual MapReduce jobs represented on a JobTracker. The data is stored in a way that's easily queryable, so we can do historical trending over a given application, or even over a given user or cluster. We can also make the cluster basically smarter. We can look at historical data to do runtime reducer optimization with pig instead of just guessing based on what we see coming in that particular runtime. And finally, it gives us a scalable archive where we can store the data forever. We currently have over 12.5 million jobs and 4.5 billion tasks plus attempts stored in this system. And that gives us the capability to later do any kind of ad hoc analysis that we want. So let's take a look at key concepts in hRaven. The first few of these are pretty self-explanatory. Obviously, you have a cluster that you run MapReduce jobs on. Each one of those clusters has a unique identifier in hRaven. You have a user. A MapReduce job has to be run by a user. And then we have an application, and that's what we use to describe a pig or Scalding script that an end user actually runs. Now, every time a user runs their pig or Scalding script, they generate a flow, which is what we call the DAG of jobs that are actually executed on the cluster. And finally, a pig or Scalding script itself is not static. That may change over time, and as the user edits that and makes structural changes to it, that'll generate a new version in the system. And by storing the versions, we can then do comparison to see, did this optimization have the desired effect, for example? So let's take a closer look at application flows. So we have our MapReduce user, Edgar, and he has his pig application that he wants to run. So he runs that on the cluster, and it generates a DAG of 4 separate MapReduce jobs. So together, that given run of the application at 10:01 a.m. is a single flow. If Edgar, again, runs the same script, say an hour later, that'll generate a new flow. Again, 4 MapReduce jobs that executed on the cluster. Now, each of these flows is stored by hRaven into HBase. And the key takeaway is that the data is ordered such that all 4 jobs in this flow are stored consecutively as rows in HBase. So this allows us to easily do aggregates and basically view the overall statistics or resources consumed by the flow together instead of just looking at individual jobs. Now, when Edgar runs his application again for a second flow, that's again stored. But within an application, flows are sorted in reverse chronological order. Now, this has 2 important benefits. It allows us to very easily see the most recent flow that's been run, which is often what the user is concerned with. And it allows us to easily do historical trending over the most recent times that the given application has been run as well. So as we've seen, all of the jobs are stored in a flow ordered together. And this allows us to easily do aggregate stats for the entire flow. Per job, we store all of the key metrics, total MapReduce tasks, byte counters for both HDFS and file bytes, and also the MapReduce slot milliseconds consumed, which is a key stat that we use to derive overall compute cost of applications.
All right, to explain a little bit of how hRaven works. So the first part of hRaven is that we need to actually get the job information into HBase itself. And that happens in 3 steps. The first step is what we call the job file preprocessor. What we're making sure first is that we turn on the feature in Hadoop that we're storing the job history files and configuration files in HTTPS itself. And you'll see in a little bit why that is. What we then end up doing is we end up doing a scan through these files and finding the jobs that we have not processed yet. What we then do is we end up writing a sequence file in the same cluster. The sequence file contains one entry per job conf and per job history file. So that's 2 entries for each job that has completed on the cluster. Now, in order to keep track of, as we're doing this processing, new jobs come in and get completed on the cluster. So we need to keep track of what we have done so far and where we are in this processing. So what we have is we have a separate table called a process record table. And on the right-hand side of the diagram, you'll see the state. So as we complete the scan, we record the time that we're starting the scan. And we create a process record in the created state. And then as we're writing the sequence file, we end up recording the sequence file and the time that we've started the scan in the process record as well, and set it to pre-processed. So this is the first step. This happens on the cluster itself where the original jobs were running, on the source cluster. What happens next is a separate independent step. The second step is the job file raw loader. So this is the stage where we need to get all of our job files and configuration files into HBase in the first place. What we now have to do is we don't have to do a scan anymore at this point because we know which files we want to load. So we have a sequence file that you see on the bottom that gets broken up into pieces doing the normal split mechanism in MapReduce. So we're running a MapReduce job where we're setting how tight we want to split this file that ends up generating. In this particular example, we're splitting the sequence file into 4 pieces, which ends up running on 4 mappers on your cluster. So we're running in parallel. The reason why we have to run in parallel is because at the rate that we're running jobs, these job files come in so fast that a single thread has a hard time keeping up. And during bursts, when lots of jobs complete and finish, it would take a long time to load. So we're doing this in parallel. The loading at this point happens from the source cluster, and on the right-hand side, you'll see the target cluster. That's an HBase cluster. So those are two independent Hadoop clusters. And the data gets loaded initially into a raw table. I'm not going to go into the details of this table. Gary will show that in a minute. After this data has been loaded into the raw tables, the job configurations and the job history, as they are, the processing record is marked as such and is set to loaded. Then the ETL process has a third and final step here, and that runs just as a MapReduce job, just on the HBase cluster itself, just on the target cluster. And what happens there is that we end up taking all these records that have been loaded into the raw table, and we ended up generating it into a history table and a task table and index tables. So what we're doing is instead of having all of the individual job history as one large file, we'll parse it apart and we shoot it out into details and create indexes. Again, Gary will talk a little bit more in a minute about what that structure looks like. After this process is done, we set the processing record to processed so that we know that this set of job has been completed. Now, intuitively, your jobs will move forward and it will increase as they go on, but it ends up being slightly more complicated than this. So I'll explain that in a little bit more detail. What you're seeing here is 3 views of the same table over time. So all the way on your left-hand side, you see the table how it is after the first run that I just went through. You see the jobs that have been completed in black. Now in the middle side, you'll see the same table, but maybe a little bit later, maybe 10, 15 minutes later when you're going through your run again. So at this point, you'll see in red that the job 1235 and 1240 till 1250 have just completed. The reason that these jobs show up out of order is because some jobs are larger than others, and the jobs show up in the history location when they're completed, but the job ID is assigned when the job is started. So it can be that jobs run longer than other jobs, and they'll appear out of order. This is important as well because we end up having millions of jobs in our raw table, and we don't want to have to scan through millions of jobs to know where we are. In our process record, we kept track of where we were, and we keep a high water mark, and then we scan down. But we do end up having to skip over certain chunks in order to get to only the new jobs that have to be processed in this particular case. And on the right-hand side, you'll see another example that in the third run, you would again have these items. So as you have some jobs that maybe run for like 24 hours, and you're running tens of thousands of jobs in a day, that range can be very large. So if you just were to split this up in a naive way and just do the range scans in equal-sized chunks, roughly, you end up having a lot of the mappers and reducers running on the HBase cluster with pretty much nothing to do, just only that one record that completed from a day ago. And then the last reducer or mapper does all of the work for all of the newly completed jobs. So what we in effect do here is that we first do a scan of all these records. We build an array locally of all of the job IDs that have to be loaded. We chunk that up in equal-sized chunks, and then we set the scans based on the start and end job IDs that we have in there.
Okay, so next let's take a quick look at the key tables in the system. There are a few other tables in this, but these really form the core of hRaven. So the job history raw table, which you've described, stores the raw serialized job configuration XML and job history logs, and it's used in the loading process. It also gives us a long-lived archive of the underlying files so that we can reprocess those as necessary. The job history table itself stores job-level data and stats with 1 row per job. Job history task stores the task-level data and stats associated with each of those jobs. And finally, job history app version stores all of the distinct versions that we've seen for a given application so that we can order those by time and later derive what the evolution was. So job history raw. This table is keyed by the simple combination of the cluster identifier and the encoded job ID. And this allows us, given a job ID, to easily re-retrieve the raw conf XML and history log files. There are just a few columns in this table. The job conf column stores the configuration XML. Job history stores the raw job history log. And finally, there's an additional status column, job process success. And this indicates whether or not the raw configuration XML and history logs have been successfully loaded into all of the other tables in the system. Now, this status column is actually stored in a separate column family, and that allows us to really efficiently scan over the records to identify unprocessed rows that still need to be loaded without scanning over the entire blobs of serialized configuration and history files. The job history table is really the core of the system. It stores job-level data. There's 1 row per job, and each row is keyed by a combination of cluster, which is the unique cluster identifier. For example, we use a short format of short cluster name at data center. The user being the user who actually ran the application, in this case our friend Edgar. Then the application identifier itself is derived by inspecting the job configuration. So we do a couple things there. If a particular configuration property is set, we take that as a definitive application ID, and that allows you as the job author to say, this is how I want this to be represented in the system. If that's not set, we fall back to doing some regular expression parsing on the MapRed job name to bring that into a consistent identifier that can easily be used in the system. In addition, we have a timestamp. Now, this is not the job submit timestamp, but the actual flow submit timestamp. So for pig, for example, this is carried through in a special configuration property, same with Scalding. The combination of cluster, user, application, and timestamp gives us the unique identifier for each flow in the system. And then since we have a separate row per job, we add on the job ID, giving us a unique row key. Now, the job ID itself, we have to parse apart in order to ensure correct ordering in the system. We still want job IDs to be ordered basically as they were generated by the JobTracker. But if you just rely on the string representation of the job ID, that's not actually what you're going to get. As soon as you hit 10,000 jobs, you're going to break apart the string ordering of the job ID. So we actually split that into two pieces, the JobTracker start time, which is encoded as a long, and the second piece is that last bit at the end, the job sequence number, also encoded as a long. The job history task table, as I mentioned, stores the task level data, and this basically extends the key structure used for the job history table. So it has all the same initial components and then appends the task ID at the end. This means we can easily join with the original job to its associated tasks. And there are two types of rows that are actually stored in this table. So it's kind of an artifact of how MapReduce jobs are run and how they're represented in the job history log itself. So there's a sort of meta row for each conceptual MapReduce task. But the way those tasks are actually executed on your cluster, you may have multiple attempts for each one of those map tasks, for example. So each one of those task attempts, which is running that given task on a task tracker out in your cluster, is represented by an additional row as well. So you can see in which cases you ran multiple attempts and which cases you did not. Finally, we have the app version table, and this is keyed on the unique identifier basically for the application, a combination of cluster, user, and application ID. And this stores all the distinct versions that we've seen for a given application. So the columns that are stored are column qualifiers are the actual versions, the version identifier. And then what's stored as value is the earliest observed timestamp for that version. So by pulling that data and then sorting by those timestamps, we can see the version evolution as jobs were run on the cluster. Now, for querying all of this data, we have a number of options. We have the basic HBase APIs, either the direct HBase client APIs or MapReduce input formats. Or we often use Pig's HBase storage as well to do kind of ad hoc processing on these tables. hRaven also provides its own custom client, Java client API, which provides some higher level abstractions around the flows, jobs, and tasks. And we also have a simple REST service that exposes APIs that we've used heavily for integrating with other systems, like building custom dashboards internally, for example.
All right, I'll talk a little bit about how we use hRaven at the moment within Twitter. So one of the more exciting things what we're using is to do automatic reducer estimation. So the part where I said, can a cluster not learn by itself? You know, there are several optimizers already in Pig that do a pretty good job in estimating how many reducers need to be there. But wouldn't it even be better if the cluster could learn and say, I can just look at previous runs of the same job and the same application, and we can recognize that now. And can we then automatically tune how many mappers and reducers, or particularly on the reducer side here, we need to set. So that's one important part in the way we're using hRaven. We're also using hRaven for capacity planning and cluster utilization. I'll be showing you a view of that in a little bit. I have a slide that shows some of that. We want to be able to know how is an application performing over time. So Gary was explaining that we can keep track of different versions. So if somebody is doing a daily job that runs over and over again, and they want to know I've made some tweaks to the script, they want to know how did that impact on the cluster. So we want to be able to show in trending how that performed. Did things go better? Did we read more? Did we write more? Were the mapper and reducer milliseconds the same? So those are all the things that we can see on a per application level instead of on an individual map reduce level. We also want to be able to identify, and we can identify a lot of common entry patterns by looking at our hRaven data in HBase. Examples of this are people running lots of jobs with very, very short mappers and reducers. That's probably not very optimal. Are people running jobs with too many mappers and reducers that they can easily consolidate, or maybe they need to break up? Are people running with a heavy skew, where only a few of the mappers or reducers take a very large amount of information? So you can imagine that not all of this information is equally distributed over the key space. So those are the kinds of things we can see. And then in general, we use it on our side when we run the cluster and administer the cluster to do ad hoc job analysis. So there's times when we want to know what has changed on the cluster, what are some of the new jobs that have appeared, what's going on, and having to browse through 50,000, 100,000, a million files on the JobTracker UI is really not going to get you the answer that you need to in the time frame that you would like to. So this is a screenshot of an internal reporting application that we have at Twitter, where we're doing lots of reporting on data and on stats, and we happen to have hooked this into our hRaven. So hRaven provides the data, and what you can see here is normal, typical counters on how many bytes are read, and in this case, gigabytes are read. So what this is showing is that we'll see an enormous growth over time that's going on our clusters, and we can kind of roughly see the ratio of HDFS files read and written, and you can see how these things graph. Here you see a couple of other examples of graphs that are produced by our internal reporting application. And on the top left side, you see a view for a pool. So these are all the jobs aggregated into a pool. And you can see that not all of the lines are equally the same at all times. So in this particular graph, you can see a spike in the green, and that indicates a spike in the read size on the mappers. And from that, we can tell that at that time, during these days, we ended up having a very large spike in reads, and that indicates that we're doing a lot of spilling. So that probably means that we've started a job on the cluster that does a lot of spilling, and we need to go look at it to see what's going on there. On the bottom side, you see the same similar view, but then drilled all the way into an application, and you can see the lines are not all the same. So this happens to be a graph where the bytes written is higher than the bytes read. So this happens to be a job where instead of you trolling through lots of information and data and you're reducing out a smaller amount, this is one of those jobs where you read through data and you end up doing joins and you end up exploding out and writing more data than you end up reading in. The other thing you can see, you see two spikes in the left on the blue side, the two very high spikes. So that indicates that the bytes that are read on the HDFS side go very high, and that kind of shows that you're having a spike on the input that you're processing. This is another view where you can see the pool usage. So the straight lines are the mappers and the reducers that are allocated to a pool, and at some point you can see them jump up a little bit because we increase the pool configuration. And then the lines underneath there you see is the mapper millis and the reducer millis that are used within that pool. So again, you can see how much capacity you're needing within the pool, and as the capacity starts going up, we realize that we have to up the capacity count in that particular pool. The other thing you can notice here is that you see very spiky behavior. The timeline on this particular graph is in months. So what this indicates is that on a weekly basis, we have a weekly job that runs on the same day in this week that takes an enormous amount of capacity and spikes over what the pool capacity is, but then the rest of the time it averages out underneath it. And then finally, as Gary mentioned earlier, we've developed a TCO cost model where we can show how much compute time costs on our cluster based on the amount of mapper and reducer millis that are used. And this is drilled in and shown here for a particular application. And again, you can see how that trends over time. And we can just show people what the cost is of running their jobs in our clusters.
So now that we've given you an overview of what hRaven currently is, we want to talk a little bit about what we're really looking to do next. First of all, currently all of the data is being loaded from archived job history and configuration files in HDFS. So it's a batch loading process. There is a delay between the time the data is loaded. For us, it's typically less than 15 minutes, but still, because one of the things we're trying to do is bridge the abstractions that are actually used by end users to the tools that the way they see things represented in the tools that the cluster makes available. What we'd really like to do is make that data loading more real time. So we'll be looking at integrating more tightly with the JobTracker or application masters so that they're in real time feeding event data directly into hRaven as opposed to waiting to parse job history and configuration files in a post-processing step. We also plan to extend a more full-featured UI that's really flow-centric. And one of the things we've been looking at closely with this is integrating with Ambrose, which gives a very rich visual representation of the DAG generated by pig jobs. We're also currently working on bringing hRaven up to speed with 2.0 so that it functions correctly. And as I mentioned, integrating more tightly with Ambrose for visualization and on the real-time side as well. And all of hRaven is now open source. We open sourced it yesterday. You can go get it right now on GitHub. So please go take a look. Give us any thoughts, ideas, pull requests you want. We'd be really happy to see them. We have a couple mailing lists set up for discussion. So please let us know what you think.
All right, I'll leave you with a final thought. So now that you've seen hRaven, this is kind of a call to action. Are you going to just drop all your job metadata on the floor? So the hRaven says, nevermore. That's the end of our story. Anybody have any questions?
What sort of facility are you looking at to go towards real-time data collection? Would you be integrating that inside of Pig and Scalding, or would you continue getting it off the JobTracker?
So one approach that we've actually kind of prototyped in a Hack Week project already is integrating with Ambrose, which makes use of the Pig progress notification listener and actually feeds events directly into a different set of hRaven tables. So that would be one means of more real-time visualization. There's still a kind of data bridging we have to do between what's actually available from the Pig side versus what we're tying it back to on the job history side. So there are a couple of challenges there. We are also looking at how we can plug into, say, the application master or JobTracker directly. Currently what happens is JobTracker gets reports in from the task trackers on tasks completed, whatever status is, and it just starts, it's writing out lines to this history log in HDFS. So I think by plugging in there, we could, instead of appending to a log file in HDFS, be feeding those events directly, streaming into HBase.
I have like two questions. Like one, you initially mentioned that you'll be using this to optimize the cluster. So I just want to know like how you guys planning to do that, to auto-tune the cluster for the jobs. And the second is, are you planning to integrate as well the hardware performance data into it to correlate, to understand how the cluster capacity is as well as performance?
Right. So we're already doing the automatic tuning, so it's not that the entire cluster gets tuned, it's that the per job settings are getting tuned. And that, an example of that is what we're already using with the Pig reducer optimization. So as the job gets launched by Pig, or before it gets submitted to the cluster, you can check with hRaven how the previous settings were and how the job performed previously, and it can then adjust the parameters as it gets submitted to the cluster. So at that point, the cluster overall, the job or Pig in that sense, is starting to self-learn and auto-adjust. And then you asked the second question.
Are we looking at integrating hardware metrics or other metrics data with the system as well?
So I think not yet, but that's a great idea.
Any other questions?
All right, thank you.
All right, thank you, everyone.